Hello, CTO Demon channel friends. Welcome back to the channel. Today, I'm going to talk about the mathematical model behind adapt wiring. Those who follow the channel know in the past few months, most of the videos in the channel is about adapt wiring, angiographic three-dimensional antegrade puncture technique. It's a type of fluoroscopic guided 3D wiring that allows the operator to puncture from the distal CTO body into the distal true lumen. Now, in this, there's one calculation we have to make, which is this calculation by dividing the near view distance from the far view distance. We calculate this by looking at how far the pre-tip wire shaft is from the center of the target in the near view, where the wire is nearest to the target, divided by the distance from the pre-tip shaft to the center of the target in the far view. In mathematical terms, we call this ND, near view distance, divided by FD, far view distance. And if this distance is a quarter, we suggest you rotate 11 degrees. If it's a half, 22 degrees. If it's 3/4, 30 degrees. And if it's same distance, 1/1, 44 degrees. Why do we come up with these degrees? What is the mathematics behind it? And why has CTO Demon never revealed the mathematics to anyone else? Well, the answer is I've been secretly hoping that one of my students or one of the viewers of the channel will suddenly send me a message and say, I've worked it out. And just the joy of working out the mathematics behind the degrees of rotation and the joy of me finding somebody who understands this would be so great that it would be worth the wait. And finally, of course, those who watch the channel and watch the shorts will know finally somebody had worked it out and sent me an email explaining the mathematics back to me, the trigonometry back to me. And the winner of the mathematical prize for adapt wiring is Shunsuke Matsuno from the Cardiovascular Institute in Tokyo. Matsuno Sensei is the first generation AP Steel Fellow from Japan, a fantastic operator. I worked with him hands-on next to me in CTO when he was much younger, and we worked together on the reverse cut paper, and now, of course, he's the one who comes back with the mathematics. So let's, this video, look at the mathematics behind the adapt wiring. Now, I'll bring you back to high school. In high school, you'll remember that there is trigonometry. And the trigonometry in a right angle triangle looks like this. There's three sides to the triangle, which in trigonometry we call the opposite, the side that's opposite to the angle you're at, adjacent, the side that's on the base of the triangle, and hypotenuse, which is the angle, which is the longest side of the triangle. Now, the angle theta can be worked out with sine, cosine, and tangent. And for the purpose of adapt wiring, we're interested in tangent. The tangent theta equals the opposite divided by the adjacent. Now, if we think about this, the opposite side, if your wire tip is turning towards the target already, the opposite side is usually less than the adjacent side. So the opposite side would be the near view, and the adjacent side would be the far view. And so it's quite easy to predict the tangent theta, the angle of theta. Now, this diagram is courtesy of Shunsuke Matsuno. This is a diagram that won him the prize that he sent to me. In this circle, you can see there's a big blue spot on the bottom left. That's the true distal lumen, the target, okay? The wire is the spot on the bottom right, okay? And you can see that there's a theta angle. So, and you can see the two views, okay? So in the far view, the FD, in the near view, the ND. And you can see theta is the angle. And basically, from the ND and FD, the opposite and adjacent, we can form a 90-degree angle triangle. And we have a theta angle. And tangent theta would therefore be ND divided by FD, which is exactly what the formula is for adapt wiring. And Matsuno Sensei has also worked out the angles for tangent theta. And it's very easy. You can do it yourself. You can use any scientific calculator, and you can press. So if you press 1 and you press the bottom button here on the left left-hand side bottom, the reverse tangent, you get 45 degrees, okay? And similarly, if you press 2 over 1 and you press reverse tangent, you get 27 degrees, etc., etc. So 37 degrees and 14 degrees for 1/4. And so this is again the chart given to me by Matsuno Sensei, and you can see if the near distance divided by far distance is 1/4, the theta is 14. Near distance divided by far distance is 1/2, theta is 27. Near distance by far distance is 3/4, theta is 37. And if they're the same, theta is 45, as we all know. Some of the more clever students will ask me then, Cecil Demon, but your rule is 1/4 is 11, half is 22, 3/4 is 33, and 4/4 is 44. It doesn't match the theta, and you're absolutely right. And the reason it doesn't match is I've did a little bit of compensation, because the temptation to do the secondary rotation is always to rotate too much. We always rotate too much. So I've subtracted a little bit from the theta so that to take account of this. Besides, 11, 22, 33, and 44 is very easy to remember. And so that is why my rule is 11, 22, 33, 44. In fact, if you put this table we look at here, we can work out the actual theta angles, 14, 27, 37, and 44 on the second column, against the 11, 22, 33, 44 rule. And you can see 11 is actually 3 degrees less than 14, okay? 22 is actually 5 degrees less than 27, okay? 33 is 4 degrees less than 37, and 44 is 1 degree less than 45. So if you follow the rule, you'll be a little bit less, but because of the temptation to over-rotate, you'll be about right. You remember, there's also a clock face model that I talk about. So this is easy for you to use your brain to imagine how much you need to turn, because 2 minutes roughly corresponds to 11 degrees, and 4 minutes to 22. That's why I say. But of course, we all know 2 minutes is actually 12 degrees, which is 2 degrees less than 14. Okay, 4 minutes is 24 degrees, which is 3 degrees less than 27. 6 minutes is actually 36, which is actually 1 degree less than 37. And 7.5 minutes is 45 degrees, exactly the same. So if you use the clock face in your mind to turn the wire, you're going to miss by around 1 to 2 degrees, but it's less. The temptation is to turn more, so you'll be very close to the target. So that's the reason why we use the clock phase, and we use 11, 22, 33, 44, and the mathematics behind it. So I hope this mathematics all makes sense to you, and I hope having a mathematical basis helps you understand why it works. But the mathematical basis behind adapt wiring is very important, because it gives a very robust and accurate rotation of the wire. With that accurate rotation, you can successfully puncture a distal cap. And so I wish you all the best as you try out the adapt wiring in your cases. Bye-bye.